Swayam Prabha. Digital India. Educated India.
Once the free vibration problem of a multi-degree freedom system is solved, it is possible to solve forced vibration problem of the same system. Of course, earlier we have solved a 2-degree freedom system's forced vibration, but that was with a very specific objective to its application to vibration absorber. Now, in this presentation, we would like to discuss the matter of forced vibration of a multi-degree freedom system. Now, there are a couple of approaches. One approach, of course, is a transfer matrix method, which is applied to very oftenly applied to torsional oscillation problems with a number of disks, and typically the method is known as Holz's method, and a standard textbook can be consulted to find that. What I would like to present here is a very generalized approach to the forced vibration problem of multi-degree freedom system. So, once we solve for the free vibration of a multi-degree freedom system, so we know the natural modes where I is equal to 1, 2, 3 up to n, which is the number of degrees of freedom. We also normalize the natural mode in a manner is 1. Otherwise, for free vibration, amplitudes do not have any definite value. So, to give some kind of a normalized approach, so we use this generalized mass equal to 1, and obviously in that case it will be equal to this. And of course, we know that same is the case with so therefore, now after you normalize, you get some unique values of the normal modes. Of course, you also know the natural frequency. Now, it is possible, as we will see with the approach I will present, it is possible to convert the forced vibration of an n degree freedom system into n single degree freedom systems forced vibration problem. And since single degree freedom systems have been solved and we know the solution, we can use that and then retransform the problem to get the actual desired values. So, if let us first define a modal matrix. Where the columns of this are nothing but so the columns of this square matrix, they represent the natural mode. This is the first natural mode, this is the second natural mode, and for an n degree freedom system there will be n natural modes. So there will be n columns, and obviously x1, x2, x3 it will go up to xn, so there will be n rows, and so this represents a square matrix of order n. This we call the modal matrix P. Next, transform how we transform x is so this is the way we transform and get another set of coordinates in place of x through this transformation rule, and this y are called generally the principal coordinates. Now, we know our equation of motion. Equation of motion was this is the forcing function. And of course, there are n such equations, and they are all coupled, as you know, through M and K matrices. Now, if we, therefore, as we know this, so therefore, second derivative, since P matrices are independent of time, P being a constant, P constituting constant element, so a time derivative, that is the second derivative, will lead to this. So now, or in terms of principal coordinates, we get this equation. We have replaced x2 dot by P by dot x by Py. Then pre-multiply both sides by P transpose. We get then now what will be this? If we find that P matrix is this, so therefore when we transpose it, so this first row, first column becomes the first row and so on. And here you will find, because of the orthogonality condition, all the cross terms will go, only the terms representing this and this, they will remain. And so the result of this will be so this will be, all the terms will be gone except the diagonal terms. This will be a square matrix, only the diagonal terms will be there, and because of our this normalization, all the diagonal terms will be 1. This is the unit matrix, straightforward we should write. And here again, it will be a diagonal matrix where the diagonal terms will be these, and rest will be 0. And here it will be column, a column matrix. These are the transformed. So therefore, what we are getting is nothing but some decoupled equations. The first equation will be, or what we will get, yi 2 dot plus omega I square yi equal to q I t, and I varying from 1 to up to. So you get simple equation which is for the single degree freedom system. We are getting n number of such equations. So y1, this constitutes only y1 2 dot and omega 1 square and y1 and q1. Next one is only in terms of y2, next one is y3. So they are all decoupled equations, and so therefore each one representing the solution for a single degree freedom system. So therefore we know the solution to this equation and we can find it out, and once we find out, and q also we have to find out by this multiplication. Once we find out y, once y is found out, we pre-multiply that by P matrix, and then we get the actual solution wanted, is in terms of x. So, this is the general procedure, and I will explain now the procedure in detail with the help of an example. So, this is the problem let us solve. So, there are 3 masses connected by 3 springs. This is 1 kg, this is 1 kilogram, this is 2 kilogram, this is 1000 Newton per meter, this is 1000 Newton per meter, this is 2000 Newton per meter, and mass 3 is being acted upon by an external force which is 50 into cosine 20t. So, forcing circular frequency is 20 radians per second, and the magnitude of the exciting force is 50 Newton. So, now the equations of motion of this of the 3 masses can be written as this. M 1, now in matrix form same equations can be represented. So it is now clear that we are writing the equation of motion for a normal mode of vibration. So once it is normal mode vibration, we know that each one will oscillate with same frequency and x can be written as x1 cosine omega t and so on. Since it is normal mode oscillation, so it is free oscillation, that you can see as it is 0 means this is the vibration for free oscillation. So our objective, as I mentioned, that before we solve the forced vibration problem, we have to find out the natural mode and the natural frequencies. So we have to first solve the free vibration problem. That's what precisely we are doing. So the characteristic equation now, as this can be written as minus omega square this is now, so therefore M inverse, this is the M matrix and this is the K matrix. Then M inverse will be, you can easily see even by inspection, inverse matrix will be also a diagonal matrix. So multiplying by M inverse, the equation becomes minus omega square now M inverse into K will be A matrix and A matrix in this particular case will be we can take common outside. This unit will be second square, as you know, because we are now solving a numerical problem, we have to be careful about the units. So the characteristic equation will be because these are a set of three homogeneous equations, so the determinant must be 0. That means and this, when we write in expanded form, becomes 2000 minus omega square minus 1000 0 minus 1000 so we get third degree equation in omega square. Solving this, we will get 3 roots or 3 values, and we can tell you that the 3 roots, first natural frequency will be second natural frequency will be and third natural frequency will be so 3 natural frequencies after solving this equation will be this. Now once we know the natural frequencies, now to find out the 3 nodes. So first let us find out the first node. The procedure I will show, and the same procedure will lead to other. So we have seen the equation that this equation, if you take, that means this equation, A is this, so 1000 2 minus 1 0 minus 1 3 minus 2 0 minus 2 1. For first mode, so now you put this is equal to omega 1 square. Oh, sorry, these are all square. Is equal to when you take to the other side, minus becomes plus omega 1 square. Now omega n1 square for the first mode is 139.2 . So this is the equation for the first mode. So we have to now find out x1, x2, x3 for this first mode. Now we have already normalized this x1, x2, x3, otherwise has got no meaning. Now we normalize it using that condition. You remember that x transpose m x equal to 1. So that means what we have done, x1 1, x2 1, x3 1, that is the transpose of x1. M matrix was 1 0 0 0 1 0 0 0 2. That was the M matrix, you must remember, and this was x1 1, x2 1, x3 1, the first mode, and that is equal to 1. That is normalization. So now there are 3 equations here and 1 equation here, in total 4. We don't need 4. So what we can do, use any 2 equations from here and this equation. of the set A and equation B. So let us solve the first two, let us say. So 2000 x1 minus 1000 x2 equal to 139.2 x1. The first equation will be that. Second equation will be minus 1000 x1 plus 3000 x2 minus 2000 x3 equal to 139.2 x2. That is the second equation of this. We don't need the third. We will have to use this one. And this equation is what? x1 square plus x2 square minus plus 2x3 square. So these three equations we can solve to find out x11, x21. Now since it represents a particular mode, we should give, it is not a general equation. So from this one, it has an equation of only x1 and x2. That will give us x2 in terms of x1, say. So this will give us x2 1 equal to 1.861 x1. If we now use this here, so x2 will be now in terms of x1 and x3 will be there. So here this will give x3 in terms of x1. Just straightforward. And then using both x2 and x3 in terms of this, we can get an equation in terms of x1 only, and this will give 13.811 x1 1 square equal to 1, and the result will be x1 1 equal to 0.269, x2 1 is just 1.86 sometimes of that, it will be 0.501. So we have found out x1, the first column of the modal matrix. That's now all the time we have to remember we are getting these unique numerical values because we have normalized the natural mode. Otherwise, there is no meaning of talking about amplitude in a free vibration problem. Similarly, x2 will be following the same procedure. Only thing what we have to do, we have to use for the second mode, and this is going to be the square of second mode, that is 1745.8. So the equations will be different, and solving that equation or that set of equations, we will get, again after normalization only we will get numerical values like this. And the third mode, again we will find out by using the third natural frequency 4115 in place of 139.2, that, and this equation will remain same. Then we will get the third mode, the numerical value of the and our modal column matrix this is our important matrix which will transform x into the principal coordinates y. So now therefore qt will be also found out by pre-multiplying the forcing matrix, which is nothing but this, we are not right to P, it is PT. So this will be this point 269.501.586 is the first row in place of first column. Second column will be the second row. And third column will be the third row. That is P transpose, and FT matrix, if you remember, force acting on station 1 is 0, force acting on station 2 is 0, force acting on the station 3 is 50 cosine 20. So this is FT matrix. Now after we do this, QT becomes so many Newton. This will be Newton. So the equations of motion in principal coordinate will become now three decoupled equations like this. and we know the solution of this steady state solution. Of course, we have to consider steady state solution for each one are given, and so we get from here y1 equal to so this we bring from our memory to the solution, steady state solution of this. We know that it will be f0 by, we know that 1 by r. Now, once we get this y, so therefore x will become you have to re-multiply y by t. So, you will 0.269, 0.501, and y we have found out, that is and the question is now what is the dimension? We are following the SI unit, so this dimension will be in meter. And this finally becomes so this is the solution. We find out x1, x2, x3 as functions of time. Of course, in steady state solution for a force vibrational problem, we always know that the transient will go and steady state oscillation will have to be with the same frequency, which is the frequency of. Now, so this is the general procedure for which I think. Now the question is that if there are two forces, then what we can do, we can separately solve and superimpose, because the system is linear. So that way we will get the solution by superimposing the solutions separately obtained in this form. Thus we come to the end of our discussion on systems with multi-degree freedom systems. Now, multi-degree freedom systems are obviously, as we have been mentioning, are the idea some modeling of the real system. That means a beam with various cross sections, or a machine, or a structure. We can model it in the form of a lump parameter system, which will be approximately representing the system. The number of lump parameters or the blocks we use, more number of the representing mass we utilize, obviously we can have a better approximation. So therefore, better accuracy or better results will demand larger number of masses and springs for a better approximation. However, there are situations where it is possible to not to break into lumps, but to treat the actual system as it is. So therefore, now we have to look into the cases where we don't lump the parameters like this. We treat the system as it is, like say for example a cantilever beam. A cantilever beam, if we hit, it will vibrate, we know that, or a bar or a shaft in torsional mode. So they are all systems which are very often, rather the actual systems are composed of such elements, and therefore our next attempt should be that how to handle cases where the system is not lumped as we have been doing so far, but the system is treated as it is. We will take up obviously simple cases like the simple elements like say uniform bar, uniform beam, shaft of circular cross section, and how to solve these problems exactly. So from next session we will take up the vibration problems of such continuous systems, and at least a few cases we will try to find. There will be some new concepts as you will understand, and those new concepts also we will explain in the process.